Welcome to the Cisco Network Academy Introduction to Networks course. In this video, we review Module 3, Protocols and Models. We'll explore the fundamental rules and processes that make network communication possible. We'll explore why protocols are essential for successful data exchange, how protocol suites like TCP/IP ensure consistency and reliability, and how standards organizations ensure that networks around the world work together smoothly. We'll also cover how the TCP/IP and OSI models provide a framework for understanding network communication, how data encapsulation enables data to move across networks efficiently, and how local hosts access shared resources within a network. By the end of this module, you'll have a solid understanding of how protocols, models, and standards work together to help facilitate global communication systems. Be sure to subscribe to our YouTube channel for more lessons, demos, and walkthroughs to reinforce what you learn here. Now let's get started with Module 3. Networks can vary greatly in size and complexity, but all communication relies on a shared set of rules that define how devices exchange information. These rules ensure that messages are sent, received, and understood correctly across any type of network. Simply having a physical connection isn't enough. Devices must agree on the method of communication for data to move successfully. There are three essential elements in any communication process. First, the source, which creates and sends the message. Second, the destination, which receives and interprets the message. And third, the channel or media, which provides the path for that message to travel from the source to the destination. Examples of network media include copper cables, such as Ethernet, fiber optic cables that transmit light signals over long distances, and wireless media such as Wi-Fi and Bluetooth, which use radio waves to send data. Network protocols define how messages are exchanged between the source and the destination. They determine the structure, timing, and method of communication so that devices can understand each other clearly. All network communication is governed by protocols. Without them, devices would have no common language or agreed-upon process for sending and receiving data. In simple terms, protocols are the rules that communication follows. They specify how data is formatted, how errors are handled, and how connections are established and ended. It's important to remember that not all protocols are the same. These rules can vary depending on the specific protocol being used. For example, how a web browser communicates using HTTP is different from how email is exchanged using SMTP, or how files are transferred with FTP. Protocols keep network communication organized, predictable, and reliable, ensuring that data gets where it's supposed to go in the way it's meant to get there. In any conversation, whether between people or devices, established rules or agreements are essential. These rules ensure that both the sender and the receiver understand each other clearly. Let's look at the example shown here. The top message is sent without following the rules. It's difficult to read, confusing, and may be misunderstood. Now below that is the same message properly formatted following agreed-upon rules. Notice how much clearer and easier it is to understand? Protocols make network communication possible by defining rules for sending and receiving messages. Without them, messages can be lost, misread, or delivered incorrectly. Protocols ensure the sender and receiver are identified, and that a common language and syntax is used. They define the rules for speed, timing, and delivery options, and that message encoding, size, formatting, and encapsulation are agreed upon. Some protocols handle confirmation or acknowledgments when appropriate to let the sender know a message was received. Following these rules helps devices communicate reliably, even across complex networks. In network communication, encoding is the process of converting information, like text, images, or audio, into bits, made up of ones and zeros, that can be transmitted over a network. This ensures the data can travel correctly across any network medium. At the destination, decoding reverses this process, converting the bits back into a form the receiver can understand. Encoding and decoding make it possible for devices to share information accurately. When a message is sent over a network, it must follow a specific format or structure. This ensures the receiving device can correctly interpret the information. The exact format depends on both the type of message, like text, files, or emails, and the channel used to deliver it, whether wired, fiber optic, or wireless. For example, this IPv6 packet header on the bottom right shows how data is organized for transmission over the Internet. Each field in the header provides critical information, such as the source and destination addresses, message length, and other details that help the network deliver the message correctly. Proper message formatting allows data to travel efficiently and be understood accurately. When sending data between hosts, the information must be encoded in a format suitable for the transmission medium, such as Wi-Fi or Ethernet. Messages are first converted into bits, and those bits are then prepared to transmit over the physical medium, whether that's electrical signals for copper wires, light pulses for fiber optics, or radio waves for wireless connections. At the destination, the receiving host decodes the bits to reconstruct and interpret the original message. Message timing is an important part of network communication, ensuring that data is sent, received, and managed efficiently. One key aspect is flow control, which manages the rate of data transmission and defines how much information can be sent and how fast it can travel. Another is response timeout, which determines how long a device waits for a reply when it doesn't hear back from the destination. The access method controls when a device can send a message on the network. Sometimes multiple devices may try to send data at the same time, causing a collision which can corrupt the messages. Different protocols handle collisions in different ways. Some are proactive, trying to prevent collisions before they happen, while others are reactive, providing a method to recover after a collision occurs. Proper message timing ensures reliable communication and helps maintain an orderly flow of data across the network. Messages on a network can be delivered in different ways, depending on the protocol and the intended recipients. Unicast is one-to-one communication, where a message is sent from a single sender to a single receiver. For example, printing a document to a network printer is an example of unicast. Multicast is one-to-many, sending a message to a specific group of devices rather than everyone on the network. Broadcast is one-to-all, where the message is sent to every device on the network. Some protocols, like ARP, use broadcast to locate devices. Protocols determine which delivery method is used to ensure messages reach the right recipients efficiently. Network protocols define a common set of rules that allow devices to communicate effectively. These protocols can be implemented in software, hardware, or a combination of both, depending on the network and the devices involved. Each protocol has its own unique function, format, and rules for how communication occurs, including timing, delivery, and error handling. Examples include IP and UDP for network communications, security protocols like SSL and TLS, routing protocols like OSPF, and discovery protocols like ARP. Working together, these protocols ensure that devices can understand each other and exchange data reliably across a network. Devices must use agreed-upon protocols in order to communicate. Each protocol may perform one or more specific functions to ensure communication is accurate and efficient. Some key protocol functions include addressing to identify the sender and receiver so that data reaches the correct destination, reliability to ensure that data is delivered correctly, even if the network is congested or errors occur, flow control to manage the rate of data transmission to prevent overwhelming the receiver, sequencing to make sure that data arrives in the correct order, especially when it is split into multiple packets, error detection that identifies and reports errors that may occur during transmission so they can be corrected, an application interface which provides process-to-process communication between network applications, allowing programs on different devices to exchange data. By performing these functions, protocols allow devices to communicate effectively, maintain data integrity, and enable smooth interaction between applications over the network. Networks rely on many protocols working together to enable successful communication. No single protocol can handle all aspects of sending, receiving, and managing data. For example, when you access a website over an Ethernet connection, several protocols work together. Ethernet handles the physical transmission of data over the local network. IP ensures the data is delivered to the correct device across multiple networks. TCP manages reliability, sequencing, and error detection. And HTTP provides the process-to-process communication between your web browser and the web server. Each protocol performs a specific role, and together they allow devices to communicate efficiently, reliably, and accurately. In a network, protocols must be able to work with other protocols to enable seamless communication. This is where a protocol suite comes in. A protocol suite is a group of interrelated protocols that work together to perform a communication function. Think of it as a family of protocols that work together to solve the problem of moving data across a network reliably and efficiently. Protocols in a suite are often organized into layers. Higher layers focus on application-specific functions like web browsing or email. Lower layers handle the movement of data, providing essential services that support the upper layers. By working together in a layered structure, protocol suites allow complex network communication to occur in an organized and manageable way. In this course, we will focus on the TCP/IP protocol suite, although there are other protocol suites in use, such as Novel NetWare and AppleTalk. For our purposes, understanding TCP/IP is sufficient, as it is the foundation of modern networking. TCP/IP protocols operate across several layers. The application layer, which supports programs like web browsers, email clients, and file transfers. The transport layer, which ensures reliable delivery, sequencing, and error checking. And the internet layer, which handles addressing and routing of data across networks. At the network access layer, the most common LAN protocols are Ethernet for wired connections and Wi-Fi for wireless networks. These protocols manage how data physically travels over local networks. Together, the TCP/IP protocol suite allows devices to communicate reliably across different types of networks and applications and is the protocol suite used by the Internet. It includes many individual protocols that work together to enable communication across networks. TCP/IP is an open standard protocol suite, freely available to the public and implementable by any vendor. It is also a standards-based protocol suite, endorsed by the networking industry and approved by recognized standards organizations to ensure compatibility across networks. The chart shows examples of protocols at each layer. Application layer protocols like HTTP for web browsing and SMTP for email. Transport layer protocols such as TCP for reliable delivery and UDP for faster connectionless communication. And internet layer protocols such as NAT and IP, which handle addressing and routing of data across networks. Together, these protocols form a complete suite that allows devices to communicate reliably and efficiently across the Internet. This slide shows graphically how a web server encapsulates a web page and how it is received by the client. The data passes through each layer of the network. HTTP at the application layer defines the content. TCP at the transport layer ensures reliable delivery. IP at the internet layer handles addressing and routing. Ethernet at the network access layer transmits the data physically. Standards organizations play a key role in the networking industry by creating rules and guidelines that ensure devices and technologies can work together. Open standards are essential because they promote interoperability, competition, and innovation. Thanks to open standards, devices from different vendors can work together seamlessly. For example, a Dell laptop and an Apple iPad can coexist on the same network. These organizations are typically vendor-neutral and nonprofit, established to develop and promote open standards. Their work ensures that technologies are compatible and reliable across different platforms. By supporting open standards, they help networks function smoothly and drive the advancement of new technologies. Several organizations play critical roles in developing and maintaining Internet standards. The Internet Society is a global nonprofit that supports the open development of the Internet. For example, ISOC promotes global Internet access initiatives and Internet policy development. The Internet Architecture Board oversees Internet standards and architecture. It provides guidance for protocols like IP addressing and routing design. The Internet Engineering Task Force develops and promotes Internet standards such as TCP, IP, and HTTP, ensuring devices and applications can communicate reliably. The Internet Research Task Force conducts long-term research into Internet protocols and architecture, such as exploring next-generation transport protocols or privacy-enhancing technologies. Two organizations play key roles in managing Internet resources. ICANN, the Internet Corporation for Assigned Names and Numbers, coordinates the global domain name system, ensuring that websites can be reliably found on the Internet. ICANN also manages top-level domains like .com, .org, and country codes. IANA, the Internet Assigned Numbers Authority, is responsible for allocating critical Internet resources, such as IP addresses, protocol numbers, and DNS root zone management. For example, IANA manages global IP address allocation, ensuring unique address blocks for global networks and devices. Together, ICANN and IANA ensure that the Internet's naming and addressing systems are stable, organized, and globally coordinated, making it possible for users and devices to find and communicate with each other reliably. Several organizations develop standards that ensure electronic devices and communication networks work together reliably. IEEE, the Institute of Electrical and Electronics Engineers, develops standards for technologies like Wi-Fi and Ethernet, enabling interoperability across wireless and wired networks. The Electronic Industries Alliance historically established standards for electronic components and connectors, such as serial ports and RS-232 communication. Telecommunications Industry Association creates standards for telecommunications infrastructure, including cabling systems like Cat5e and Cat6 Ethernet cables, and wireless standards used in cellular and satellite communications. The International Telecommunication Union sets global standards for telecommunication networks, including voice, video, and broadband protocols, ensuring devices worldwide can connect seamlessly. Understanding how a network operates can be complex. Layered network reference models are used to help simplify these complex concepts. A reference model provides an overview or blueprint of how networking functions. They provide a big picture view. Imagine you are in an airplane flying over the Grand Canyon. From 30,000 feet in the air, the canyon is beautiful, and you can see its full structure. But up close, whether you're whitewater rafting the Colorado River or hiking along a trail down into the canyon, the view is completely different. When you look closely at how network communication works, things can get complicated. Reference models are like that 30,000-foot view of networking. They show how the layers and protocols work together without drowning in all the complex details. This course examines two common reference models, the OSI reference model, which has 7 layers, and the 4-layer TCP/IP reference model. In this course, we focus on these models to help understand how data travels across networks from a high-level perspective. Using a layered reference model offers several important benefits for networking. It assists in protocol design because protocols at each layer have clearly defined information to act on and a defined interface to the layers above and below. It fosters competition by allowing products from different vendors to work together seamlessly. It prevents changes in one layer from affecting other layers, so new technologies or capabilities can be introduced without disrupting the entire network. It provides a common language for describing networking functions and capabilities, making it easier for engineers, developers, and students to communicate and understand network operations. Overall, layered models make network design, implementation, and troubleshooting more organized, flexible, and understandable. Let's take a closer look at the OSI reference model. It divides network functions into 7 layers, each with a specific role in communication. From top to bottom, the layers are the application layer, which is closest to the end user, providing services directly to applications like web browsers or email clients. The presentation layer is responsible for how data is presented, including formatting, encryption, and compression. The session layer manages sessions or connections between devices, keeping them open and synchronized. The transport layer ensures reliable data delivery, sequencing, and error checking. The network layer is responsible for communication between different networks using logical IP addresses to route data. The data link layer uses physical MAC addresses to deliver messages within the same network. And the physical layer handles the transmission of raw bits over cables, fiber, or wireless signals. To help remember the order of the layers from top to bottom, you can use the mnemonic "all people seem to need data processing." Each layer relies on the one below and provides services to the layer above, forming a structured approach to network communication. The TCP/IP reference model is a simplified framework for understanding network communication using 4 layers. Just like the OSI model, each layer has a specific role in moving data across networks. From top to bottom, the layers are the application layer, which provides services directly to applications like web browsers, email clients, and file transfers. It combines the functions of the OSI application, presentation, and session layers. The transport layer, which ensures reliable or fast delivery of data using protocols like TCP and UDP, handling sequencing, error checking, and flow control. The Internet layer, which is responsible for logical addressing and routing, using IP addresses to deliver data between devices across different networks. And the network access layer, which combines the OSI data link and physical layers and manages physical transmission over local networks using technologies like Ethernet and Wi-Fi and MAC addresses for delivering data within the network. Some references show a 5-layer TCP/IP model, which splits the network access layer into 2 separate layers, but this course focuses on the standard 4-layer version. A simple mnemonic to remember the layers is all the Internet needs. This model provides a practical framework for understanding real-world networking and how the Internet operates today. While both the OSI and TCP/IP models describe network communication, they differ in structure and detail. The OSI model divides the network access and application layers of the TCP/IP model into multiple layers, providing a more detailed framework for understanding each function. In contrast, the TCP/IP protocol suite does not specify which protocols must be used to transmit data over a physical medium. OSI layers 1 and 2 focus on the procedures required to access the network media and the physical means of sending data, such as cables, fiber, or wireless signals. By comparing the 2 models, it's easier to understand both the practical TCP/IP implementation and the conceptual OSI framework for network communication. Encapsulation is the process of packing data with the necessary information at each step so it can travel across a network and be understood by the receiver. When sending data across a network, large messages can be difficult to manage efficiently. That's where segmentation comes in, working hand in hand with encapsulation. Just like encapsulation wraps data with protocol information at each layer, segmentation breaks a large message into smaller, more manageable pieces, called segments. Multiplexing then allows multiple streams of segmented data to be interleaved and sent over the network at the same time, making the process even more efficient. Segmenting messages provides 2 main benefits: increased speed by allowing large amounts of data to be sent without tying up the entire communication link, increased efficiency. If a segment fails to reach its destination, only that piece needs to be retransmitted, not the entire message. By segmenting and encapsulating data, networks can send large messages quickly and reliably. When a large message is broken into segments, it's important that the pieces arrive in the correct order. Sequencing is the process of numbering each segment so the original message can be accurately reassembled at the destination. In the TCP/IP suite, the TCP protocol is responsible for sequencing, ensuring that even if segments arrive out of order, they can be put back together correctly. Sequencing ensures reliable communication for protocols that require it, maintaining the integrity of the data being sent. As data passes down the network layers, each protocol adds its own information in a process called encapsulation. At each stage, the resulting unit is called a protocol data unit, or PDU, and its name reflects its role at that layer. In the real world, most network professionals simply refer to all PDUs as packets. However, for this course, it's important to differentiate between them to understand how data moves through each layer. Using TCP/IP terminology, PDUs are referred to as data at the application layer, a segment at the transport layer, a packet at the Internet layer, and a frame at the network access layer. This is encoded into bits and sent through the physical medium. A simple mnemonic to remember the order is, "Don't some people fear binary?" Understanding PDUs in this way helps us track how data is prepared, transmitted, and reconstructed across a network. When a web server sends a web page to a client, the data doesn't travel as a single block. Instead, it is encapsulated layer by layer. First, the web page data is prepared by the HTTP application protocol. This data becomes the payload data for a TCP segment, which adds transport layer information like port numbers and sequencing. Next, the TCP segment is wrapped inside an IP packet, which adds the source and destination IP addresses so the data can be routed across networks. Finally, the IP packet is placed inside an Ethernet frame, which adds the source and destination MAC addresses and prepares the data for transmission across the local network. At the receiving client, each layer is de-encapsulated in reverse order, eventually reconstructing the original web page for the user. This layered encapsulation ensures that data can travel reliably across networks, reaching the correct device and application in the proper format. Proper addressing is essential for accessing data on a network because it tells devices where to send and receive information. Both the network and data link layers use addressing to deliver data from the source to the destination, but they serve different purposes. At the network layer, source and destination addresses, known as IP addresses, are responsible for delivering the IP packet from the original source device all the way to the final destination, even across multiple networks. At the data link layer, source and destination addresses, known as MAC addresses, are responsible for delivering the data link frame between two network interface cards, or NICs, on the same local network. By combining these two layers of addressing, networks ensure data can be accessed efficiently and accurately, both locally and across distant networks. At the network layer, each IP packet contains two key addresses that guide its journey, the source IP address and the destination IP address. The source IP identifies the sending device, the original source of the packet. The destination IP identifies the receiving device, the final destination of the packet. These addresses allow the packet to reach the correct device, whether it is on the same local network or a remote network across multiple hops. An IP address is divided into two main parts, the network portion and the host portion. The network portion represents the network group that the IP address belongs to. Every device on the same LAN or WAN will share this network portion, allowing routers to direct traffic to the correct network. The host portion identifies a specific device within that network. Each device on the network must have a unique host portion so that data can reach the intended device accurately. When devices are on the same network, the source and destination will start with the same number in network portion of the address, as shown here for PC1 and the FTP server. When devices communicate on the same Ethernet network, the data link frame uses the actual MAC address of the destination NIC. MAC addresses are physically embedded into the NIC, making them a form of local addressing. The source MAC address is the address of the device sending the frame on the local link. The destination MAC address is always the address of a device on the same local network, even if the packet's ultimate destination is on a remote network. This system allows devices to reliably deliver data locally, while higher layer protocols, like IP, handle routing to distant networks. What happens when the actual destination isn't on the same LAN, when it's on a remote network instead? Let's take an example. When PC1 tries to reach a web server located somewhere across the internet, it can't send data directly to that server's MAC address because they're not on the same local network. This is where the network and data link layers work together. The network layer, using IP addressing, identifies that the destination is remote. It then forwards the packet to the device responsible for getting it closer to its destination using the default gateway router. The data link layer then takes over to deliver the frame locally to that router, using the router's MAC address as the destination. In short, even when communication is remote, the data link layer still handles local delivery, while the network layer ensures the packet finds its path to the final destination. When the source and destination have a different network portion, this means they are on different networks, as shown here for PC1 and the web server. When the final destination is on a remote network, the network layer provides the data link layer with the local default gateway IP address. The default gateway is the router's interface IP address that belongs to the local area network. You can think of it as the doorway or gateway that leads to all other remote networks. Every device on the LAN must know the address of this gateway. Without it, any traffic meant for remote networks would never leave the LAN. Once PC1 forwards its data to the default gateway, the router takes over. From there, it begins the routing process, determining the best path to deliver the data to its final destination, whether that's another office across town or a web server across the world. At the data link layer, addressing is local. It only applies to the connection between two directly connected devices on the same link. For example, when PC1 sends data to its default gateway, the MAC addresses used are specific to that local connection. The source MAC address belonging to PC1 sends the frame. The destination MAC address belonging to R1, the default gateway, receives the frame. Router R1 will de-encapsulate the frame to access the IP packet contained inside, then will make a routing decision, and encapsulate it into a new frame and send it out the exit interface to the next router. As the data moves from one link to another through routers and other network segments, the Layer 2 addressing changes each time to reflect the new local connection. However, the Layer 3 IP addressing stays the same from the original source to the final destination, ensuring end-to-end delivery across the network. As we wrap up Module 3 of Introduction to Networks, let's reflect on what we've covered so far and why it is important. In this lesson, we explored how network communication depends on well-defined rules, protocols, and models that keep data moving smoothly from one device to another. We examined reference models, the OSI and TCP IP frameworks, which give us the 30,000-foot view of how protocols and layers work together. These models make complex networking concepts easier to design, explain, and troubleshoot. We covered protocols and the TCP IP protocol suite and how multiple protocols must cooperate to handle addressing, reliability, flow control, sequencing, and application interfaces. We looked at encapsulation and protocol data units, how data becomes a segment, then a packet, then a frame, and finally bits for transmission, and how that wrapping and unwrapping moves data safely through the layers. We also covered addressing, logical IP addresses for routing between networks, and physical MAC addresses for local delivery, plus the role of the default gateway in forwarding traffic to remote destinations. Finally, we explored how data is delivered to different types of recipients through unicast for one-to-one communication, multicast for one-to-many communication, and broadcast for sending data to all devices on a network segment. At this point in the Cisco Networking Academy Introduction to Networks course, students take the checkpoint exam covering modules 1 through 3. Let's review what you need to know and study in order to successfully pass this first checkpoint exam and demonstrate your understanding of the core networking concepts covered so far. Expect a few questions from Module 1. Make sure you understand the different types of Internet connections. Be familiar with common network types like LANs, WANs, and wireless networks. Don't forget the 4 basic characteristics of a reliable network: fault tolerance, scalability, quality of service, and security. Know what each does. There are a lot of questions that come from Module 2. If you haven't been doing the labs, now's the time. Hands-on practice really helps. Going into the checkpoint exam without this really puts you at a disadvantage. Know the Cisco iOS command modes and their prompts. Know which mode you need to run the enable command along with other basic configuration commands. Understand what an SVI is, what it's used for, and how to configure one. Be clear on access methods, both in-band and out-of-band, and the difference between Telnet and SSH. Module 3 tries to throw a lot of information at you, and roughly half of the questions on the exam come from here. Make sure you know the reference models, and especially which OSI layers line up with the TCP IP model. Encapsulation is key. Know which PDU goes with each layer and what each PDU is responsible for. For instance, know that IP addressing is contained in the IP packet. Remember that a frame is the PDU at the data link layer and carries MAC addresses. Review all the PDUs and their roles so you understand how data moves across the network. Don't forget to study the application layer protocols used in the TCP IP protocol suite like HTTP, SMTP, and FTP and understand what they do. Know what a default gateway is and what it does. Study how MAC and IP addressing are both used to communicate across local and remote networks. Go over these topics, get some practice, and you'll be ready to tackle the modules 1 through 3 checkpoint exam with confidence. So, what's next? In Module 4, we're starting our journey up the protocol stack, beginning at Layer 1, the physical layer. We'll explore the hardware and media that make networks possible, from cables and connectors to wireless signals. You'll see how bits travel across the network, how devices physically connect, and why the physical layer is the foundation for everything that comes next. Get ready to see networking in action right at the very beginning of the journey. Make sure you click that subscribe button, and let's keep building your networking knowledge one step at a time.